Hi there students, this is Dr. John, your physics and math professor, and today we're continuing another video on optics. Specifically, I'm going to talk to you about sign convention, how you know what is positive and what is negative, and how to use the optics formula as well. Just quickly review the 4 different cases that we have here for thin mirrors and thin lenses. On this side, I've drawn the converging mirror and lens, and on this side, the diverging mirror and lens. So just to review really quickly, here we have the object. Objects are measured positively if they're upward, just as it should be, which is sort of your token word to remember, as it should be. This would be measured positively because it's up from the line, and then we take one line over here, hit the mirror, come back and hit the focal point and continue on. That's the purple line up there. The other one, we come straight through the center, come over here. I would really extend this mirror further and it would hit the mirror somewhere down there. I just didn't have enough space on the board here, and it would reflect straight back. Both of those would meet right there and would form an image. The image is upside down, so this has a negative height. I've labeled the object as O, the image is I. The center of curvature, which is the center of the curvature of the mirror here, at C. F is half the distance to the center of curvature. We measure always from the center of the right here at the mirror, or right here at the center of the lens. Now, since these are really thin, there's practically no difference between the edges here and the center. It's basically a straight line. Same way over here, same way over here. So we measure basically from that point right there. The focal point is half of the center. We'll often draw a second focal point and a second center over here, especially we do that for the lenses. Notice we tend to do that for the lenses. I did that for all of them just so you get a reference for the various distances involved in that. I've also drawn a wall here, the checkered line here for the mirrors, or a wall. There's nothing really on this side. Nothing can really happen on this side. Light can't actually go onto this side. So here we have a real image. Why do we have a real image? Because it's on the side of the mirror that light should go. Light should go onto this side. That's what you expect of a mirror. So it's a real image. It's upside down as well. Now here's for the converging lens. Here we have the one line, the purple one. It comes in and hits the focal point and then continues on. The other one we draw through the center of the lens. Here we drew it through the center of curvature for the mirror, but we draw it through the center of the lens here, and it continues on. Where they intersect right here, we draw an upside down arrow. It is a image, and this here is a real image. Notice I again use the letter I for image and O for object here. It's a real image. Why is that? Because it's on the side of the lens that images should be formed. Light should go through a lens. So if an image is formed on this side, it is a real image. These are both converging. That means the light that hits the mirror in various places will all converge or come together basically at the focal point here. It all tends to bring light together. This one over here too tends to bring light. If we had another ray coming here, it would bring light up here to the focal point. It all tends to converge light. Light converges all into one spot. For a mirror, it's where it should be on this side. For a lens, it's where it should be on this side. Now here, these are diverging. What do I mean by diverging? Well, take a look at this one ray of purple light here. Hits the mirror here, and it reflects straight away. If we had another one that came in here, it would reflect that way. Notice the light gets diverged. Now, if we draw a dotted line, a dashed line coming back, it actually seems to be coming from this focal point here. And again, radius of curvature of the mirror right here, the focal point, the focal distance would be half of the distance to the center. So this is marked as the focal point. Light seems to be coming from here as it diverges away. So this here is a negative length of focal length, this focal point here, because light seems to be coming from it. This is a positive length for the focal point or the focal length because light is coming toward it. Also, this focal point is on the right side of the mirror. I don't mean right as in right left, but the correct side as far as where light should be reflected, where light should be focused. It's on the mirror side. It's on the side over here. And this one, light should go through the lens. So this focal length here is positive. So here we're dealing with negative focal lengths. Here we're dealing with positive focal lengths. This one over here, and then the other ray of light, we take straight to the center of curvature on the other side, the actual center of curvature for this lens, and it will reflect straight back. So we get the intersection right there. This, of course, the image over here is on a side of the mirror where nothing should go. There's no light that actually goes here. So this is a virtual image. It happens to be upright. So it has a positive height if we're measuring the height. So this over here is a diverging lens. Notice this purple ray of light comes over here. It goes up like this. And if we mark it back with a dotted line, it's going to come back to the focal point, which means the light, this ray of light, seems to be coming from the focal point. if we take another brown ray of light here and go right through the center of the lens, they intersect right there and we get an image. Now this image is where it should not be. You should not have an image on this side. Just think about it. Yes, sometimes you do have an image on this side of the lens, but think of light should go through a lens. That's how it should be, which means this is on the side it should not be, which means it's a virtual image and it's not a real image. These are real images. These are virtual images. Now let's look at the calculations using the lens formula, and here's the magnification formula. I'm going to do an example for each of these, and I've made the measurements all the same here. So what I've done here is I've created, say this is a distance of 5. This is a distance of 10 to the center, and the same over here. This would be 5, this would be 10, and this would be 15. So I'll just write them in here, 5, 10, 15, and these also are a distance of 5 and 10. So I've created the same distance, and same over here, 5, 10, 15 for all of them, and 5, 10. I made it so that the distances are roughly correct. And by the way, just a tip here, the height of this thing is far too high for the distances here. One of the stipulations for a thin lens or a thin mirror is that the height of the object is much less than the distance to the center, the distance to the focal point. It has to be about 1/10. I'll show you that in another video. So this should be really tiny. So I've exaggerated the height here just to show things more clearly. So let's use this lens formula now for these two different things. I'm going to start off by doing this here with a converging one. So how do we do this? Well, we take the focal length, the object, and the image. All of the objects here are positive. That is, they are a positive distance from this lens in that the light is coming from them. So you'll always measure that as positive if the light is coming from the object, which it will be in practically all cases that you'll be dealing with. So this has a positive number. The focal length for a converging lens is positive. That means light is coming toward that focal length. That's where it's gathering. So it's actually gathering there. So it's going to be a positive number for that. And then we're going to see what the image is. So let's take a second to calculate these two. So here we have the focal length. I said that was positive. So it's going to be 1/5. That's going to be equal to 1/15 plus 1 over the image. Sorry that my ones and my eyes look very similar, but hopefully you can tell the difference. Now notice here, I chose these numbers specifically because they're easy to work with. We could relabel this as 3/15. So I could make this 3/15, multiply the top and the bottom by 3. Now I can take this, move it to this side. I'll take 3/15, subtract 1/15 from this side. I'm going to be left with 2/15. So this here is going to be 2/15, and that's going to be equal to this, 1/I. Now, I can take both of these and flip them, and I'm going to have I is equal to 15/2, or 7.5. So that would be the distance to the image. Notice it's a positive distance. I'll just erase this so that I can have room to work here. I'm going to mark that in here. So this distance over here from the lens to the image, actually I did this calculation for this one, didn't I? From the mirror to the image is 7.5. Now notice this distance is 5, this distance is 10, so the marking here, the length that I've done is pretty well correct. So this is 7.5. This also right here is 7.5. Now notice I used the measurements for this, but I could have used them for this just as well, because the focal length here also is 5, the distance to the object is 15, and if I use that same calculation, I'm going to also get the image for 7.5. Now you might look at these diagrams and say, well, we've got 4 different things to memorize. Well, really you don't. You only have 2. These 2 are completely analogous to each other. If I put the object here and the object here, notice that the image forms at 7.5 here. 7.5 here. It's between F and C. It's between F and C. And they're both upside down real images. So the magnification is even the same. So these two are completely similar to each other. It's just this one here forms on the lens side, on the side where an image should form for a lens. This one forms on the side where an image should form for a mirror. So this distance is positive here with the mirror, and this distance is positive here with the lens because it forms where it should be. So now we're going to calculate the image distance for the diverging mirror and the lens. Now, what do I use for the focal length for that? Well, notice for both of these here, the light does not actually converge there. It seems to come from there, which is the opposite of what a focal length should do. And the same over here. So the focal length for diverging lenses is negative. So I'm going to use 1/-5 is equal to 1/15 plus 1 over image. Again, I can take this to the side. I can make this 3 over 15. And then I can take this, subtract this, and I'm going to get minus 4 over 15. If I take this to the other side, 4 over 15. This negative sign, of course, doesn't need to be in the bottom there. It can just be out front there. So now I have 4 over 15, a negative, is equal to 1 over I. I can flip both of them. I'm going to get I is equal to negative 15 over 4. Is equal to negative 15 over 4, which is approximately, this is 16 over 4 would be 4, so it's approximately equal to minus 4. Let's go over here and put that in here. Notice the distance from the mirror to this F here, this focal point here is 5. And this, I drew this just inside there, which would be about minus 4. So this distance here is minus 4. And also this here, notice I drew this here. This is minus 4 as well. So notice again, just like I showed over there, this image here is the same distance for the mirror as it is for the lens, because these again are symmetric, or they're analogous to each other. It's just that mirrors should reflect, lenses should let light through. But in this case, the image is on the side where it should not be, which means that the image is a negative length. It's also a virtual image. This one over here, for a lens, images should be on this side. You tend to think that they should be, but it's on that wrong side, the wrong side for what we think they should be. So it's a negative distance, and it's also a virtual image. So now let's just do the last thing over here to do the magnification. Now, doing the magnification, we can do it two different ways. We can use the heights of the image and the heights of the object. The image and the object are measured positively up, negatively down, just as they should be. But we don't have those. But we do have the distance to the image and the distance to the object. So let's now take these two, since remember they're completely analogous to each other. Let's take them and try to figure out the magnification. We know the magnification is going to be less than 1 because the height of this one is less than this, but the magnification should be positive because they're both in the upward direction. So the distance to the image is roughly minus 4, but remember it was exactly minus 15 over 4. So let's use this correct one here, minus 15 over 4. And we want to divide that by the distance to the object, which is 15. And of course, we have to put a minus sign in front of it. But if we put a minus sign in front of it, there's going to be two negatives. So those will cancel out and give me a positive. I don't need this anymore. So now 15 divided by this, when you divide by 15 like this, you flip and multiply 1 over 15. The 15s cancel, and you get this equal to 1/4. So here the magnification is 1/4. It's a positive number, which means they're both upright, and it's 1/4 of the whatever height this is. This should be 1/4, which my ray diagrams are approximate. The calculations are exact. Do both of them and you'll be able to compare them. But it looks like my diagram is about right on that. And then here's the actual calculation. So the magnification is 1/4. Let's do the magnification for this side over here as well. The magnification is equal to negative sign in front, 7.5 divided by 15. Remember, this is half of this. So this is going to be minus 1/2. Like that. And notice, yes, this one is upright. This one's flipped upside down. This one's upright. This one's flipped upside down. There's the minus sign. And it's about half the height, so it seems to work pretty well. So there you have the magnification for both of them. And we used this formula. Just to review sign convention, focal lengths, the focal distances are positive if light is converging there, which means they're positive for converging mirrors and lenses. And these two are completely analogous to each other. The distance to the object is positive if light is coming from there, which it will be in practically all the cases that you have. So the distance to the object is positive. The distance to the image is positive if it is on the side where it should be. I'm using that to help you remember it. For a mirror, you would think things should be reflected on this side. So if the image is on this side, the distance is positive. For a lens, if the image is on this side, that distance is positive. So let's take a look at this case over here. The distance to the focal point is going to be negative because light seems to be coming from there, not focused there. And also, if you also want to remember, diverging mirrors and lenses have negative focal lengths. The distance to the object should be positive because light is coming from there. And the distance to the image, well, the distance to the image will be negative if it's on the wrong side. So here, The mirror should not form an image over there. No light actually goes over there, so that's a negative distance. And you would think light goes through a lens, but here it's on the wrong side, so it's a negative distance to the image. I hope that helps you. If it did, like and subscribe. Also, check out my website where I'll have a bunch of study sheets like this, free to download, no cost obligation. You don't need to register or anything. I just want to make you the best at physics and math that you can possibly be. So I'll see you in the next video. Bye-bye.